Hello again. Some of my students wanted me to go through reaction mechanisms and perhaps rationalize why they are named what they are named, more or less. So here we go. Some of it might be in module 4, but remember when you sit in paper 2 is organic chemistry. From the beginning to the end, module 4, all the way down to module 6. So let's start with the first chemical reactions that I start with my students. I don't know whoever is watching these video clips, but it doesn't matter when they were taught. What I'm about to go through will be part of the OCR syllabus. First of all, let's talk about free radical substitution. Let's say you have a, I don't know, methane molecule. You see, the reason that alkanes are just burnt as fuels, unfortunately, methane and ethane are natural gases, and propane and butane, petroleum gases. And then it goes all the way to pentane and hexane. From hexane onwards, it begins to turn into more or less a liquid feature. Octane, of course, is petrol. And when the carbon chain becomes longer and longer, then they are used for other purposes, diesel fuel, jet fuel. All of these compounds that have taken millions of years to be produced under severe conditions of high pressure and high temperature. What do? We just burn them. So, but then imagine if some people say, well, can we do something better with them? Can we convert them to something slightly more useful? Well, yes, there is. But you see, the reason that we burn these guys is because they lack any functional groups that we can work with. If they had a functional group, then we can change that functional group to something else, and then that something else to something else. You see, if we have methane, we can convert methane to chloromethane by free radical substitution. By nucleophilic substitution, we can convert chloromethane into methanol, which all in a sudden is a liquid. We can convert by oxidation, we can convert under distillation condition, we can convert to methanol, to aldehyde. If you want to further oxidize it, you convert it into methanoic acid. And I'm just using one example here. Yeah. I mean, this guy is far more important than methane. It's a liquid fuel. It's a two-step reaction. How did we produce it? Because we introduced a chlorine as a functional group, then OH can go and displace chlorine, sit next to it, and then turn into an alcohol. Now, if you recall your primary, secondary, tertiary alcohol, that is an example of a primary alcohol, isn't it? And then, of course, if you oxidize it under distillation conditions, so as soon as the aldehyde is made, we actually take it out, then we've made methanol. So methane, chloromethane, methanol, methanal, methanoic acid. And then if you react methanoic acid with the methanol that you produced earlier, then you produce the corresponding ester, isn't it? So you have CH3OCO, CH3. I beg your pardon, I'm putting more carbon than I should. Methyl methanate, an ester. So from a humble beginning, all in a sudden you produce something which might have a nice fruity smell. And at each stage, of course, we have to spend energy, we have to use chemicals in order to get to these points. But then, so why do they do it? Because by doing it, they make a lot more money, and they're making far more viable, far more important compounds. Remember, liquid fuel is enormously important. And if we can make it ourselves, so much the better. Now, let's explore each of these things very, very quickly. Free radical substitution, right? So the name free radical comes about. Let's say you've got methane and you want to convert it to chloromethane. The first thing that you have to do, which is called initiation. Obviously, you initiate the whole thing, isn't it? So that's step number one. Imagine you want to react it with chlorine, for example. So you get your chlorine molecule. I'm purposely writing a displayed formula because I want to show the reaction mechanism. The condition that is required for this is UV light. UV light, the energy of the light, UV light strikes at this bond. And as a consequence, what happens, it results, you see, every one line that you have between atoms, it's a bond, yeah, non-metals. And a bond comprises of two electrons, one that came from this one and one that came from the other one. So what does the UV light do? Provides the energy for this bond to break. So basically, these guys will take their own electron and go their own way. The electrons that they're sharing, covalent bond, remember? Now they get their own electron back. So basically, a one-sided arrow that I'm drawing, and you have to be very careful with these arrows. That one-sided arrow says one electron that I was sharing with this guy, I'm taking back. One-sided arrow, movement of one electron. And it's referred to as homolytic fission. It breaks, but then it's homolytic because each of these guys will get a share of their own electron. They get one electron each. So what do we produce? We produce two chlorine, basically to you and me, two chlorine atoms. But sometimes we put dot on the, just to show that there are free radicals. As soon as you hear the word free radical, it means species that are extremely reactive. Why are they extremely reactive? It's quite obvious why they are. They were very happy when they were forming a covalent bond, stable, yeah, relatively speaking. But now there are atoms, they only have 7 electrons in the outer shell. They want to become stable again. So anything they find on their path, they react with, and they are not particularly choosy. So when you put methane on its path, again, let's put a displayed formula there. When you put methane here, so what happens? Now you've got chlorine free radical. Now that chlorine says to one of these carbon-hydrogen bonds, hey hydrogen, come and make a bond with me. And then the carbon now takes its electron back. So what do we have now? CH3. Now this guy has turned into a free radical. And then the other product is HCl. So that section is referred to as propagation. Propagation. To propagate means to make more. Yeah. But this is propagation part 1, and part 2 is the CH3 dot now goes in the same reaction chamber and reacts with a normal chlorine molecule. Again, watch the arrows as to where they come. Arrows, I tell this to my students all the time, come from where electrons are. Don't take them from midair. Don't take them from, if you drew that from hydrogen, if you drew that from anywhere else, if these arrows came from chlorine, you just lose a mark. Because the electrons are coming from the bond, where the electrons are. So the same, well, I suppose in a way that you can get easy marks by doing reaction mechanisms, or just drawing a few arrows here and there that takes you a few seconds, you can just as easily lose them if you draw them wrongly. And the examiners don't take prisoners. Do you understand? So what did we get? CH3, Cl. This is the product that we were after. And what else do we produce? Another chlorine free radical. So the reason it is called propagation is because the reaction continues. This will go and find another methane molecule in the chamber and will turn it into that. The last part, the third part, termination, obviously the name's on the tin, is when instead of free radicals going and reacting with normal molecules like methane or chlorine or whatever, they actually react with one another. So what are the possibilities? What could we have in the reaction chamber? Well, in the reaction chamber, obviously, we have chlorine-free radicals, don't we? So if two chlorine-free radicals come and react with one another, they produce CO2. That's one possibility that terminates the reaction, stops the reaction. The other possibility is that you have chlorine-free radical as well as CH3-free radical. Remember, these are just the examples, simple example I'm using now. And then you do produce, say, the intended product, but you don't produce a chlorine-free radical to continue the reaction, do you? So the reaction stops. And then the strangest of them all is that when two free radicals come together, two methyl free radicals, two alkyl free radicals come together, and they produce C2H6. Now you might be thinking, if you analyze this, where did C2H6 come from? Was it contaminated? No. It is in the chamber as a consequence of termination of two smaller alkyl functional groups that you had. So, so that is free radical substitution. I'll do another one in this particular clip, and then I'll do the other ones in another clip in order to make it a little bit shorter rather than too long. So you can, of course, go back and forth with these and try to see. So the second reaction mechanism I'm going to talk about is nucleophilic substitution. Nucleophilic substitution, or sometimes referred to as substitution nucleophilic. You know, in French they say the other way around. Nucleophilic substitution. So okay, so we've got this compound over here. And when I put R, it means we don't really care what's sitting on the other side. And then we put that in a pot, and in that pot we put, say, for example, a very strong source of hydroxide ion, say sodium hydroxide, yeah? A very strong source of hydroxide ion with a negative charge and a lone pair, all right? So what is it that you have to show? The first thing that you have to do is that you have to show that the bond is polar. Carbon and chlorine have different electronegativity values. Chlorine is more electronegative. They share electrons together, but it's a very unfair sharing. Most of the time those electrons are closer to chlorine than they are to carbon. So they make that part a little bit more negative than carbon. But what about this guy? It's quite obvious. So why is it the nucleophilic substitution? What is this guy? It's a nucleophile. Why is it a nucleophile? Nucleo means a positive center. Phile in Latin means loving. Nucleus or positive loving. Why? Because this hydroxide ion has lone pair of electrons to give. It's negatively charged. So what happens? As soon as there is a positive center, if I may use another color, then it will attack that. But then, of course, carbon can't have 5 bonds. So if OH is coming in, then it's going to lose the Cl as Cl minus, isn't it? Now, the idea of SN1 and SN2, which you can learn for yourself, is not particularly in the syllabus, but I sometimes mention it in my class, is You see, there is one type that as OH is coming in, Cl at the same time is going out. I refer to this motion as analog, using my own terminology. So you have an intermediate stage where carbon will have that bond, this bond, and that bond for sure, and it's got two partial bonds. One is that it's getting shorter and shorter, the other one gets longer and longer, and eventually it's lost. And then the other approach is that it's like as soon as carbon sees OH minus, that goes out, Cl minus comes out, and then this attacks. Out, in. I call that digital, digital mode. But not in the syllabus. All you need to know is the substitution reaction as we see. So what do we have? R remains the same, carbon is the same, hydrogen is the same. That hydrogen is there, and then now you have that OH sitting over there, and then plus Cl minus. Just something to know. So basically you turn your haloalkane into corresponding alcohol. Something to note is that if you use hydroxide, then you have to write your equation like that. But if, for example, you use sodium hydroxide to do the reaction, I mean sodium is shown in the question, then you can't write Cl minus, you have to write sodium chloride. A little bit, being pedantic, but incorrect at the same time. So this is nucleophilic substitution, exactly like that. The arrow comes either from lone pair or from the negative charge. If you draw it from anywhere else, you lose a mark. If you haven't drawn your polarity, you lose a mark. If you haven't drawn that arrow, that carbon-chlorine bond in this case is breaking and the electrons are coming from the bond, if you draw that arrow slightly further down or further up, you lose a mark. It took me a few seconds drawing this and perhaps getting 3 marks. But then you can also spend 3 or 4 seconds not gaining 3 or 4 marks. Your answer could be close to the reality, close to the actual thing that you should have done, but not exactly. And if it is close but not exactly, you lose 3 marks. Okay, I think we wrap this up now, and then perhaps I do, if there are other reaction mechanisms, I'll do it in another lesson. Thank you.